Welcome to G Fun Facts Online. Our planet's weather is a constant dance of energy and water, and within this grand performance, scientists are watching two phenomena with growing interest: breathtaking megaflash lightning that stretches for hundreds of miles, and the profound shifts in rainfall that bring either devastating floods or crippling droughts. These aren't just weather curiosities. They are deeply connected, rooted in the science of atmospheric hydrology, and they are powerful signals of our planet's changing climate. Today, we're journeying into the heart of these massive storms to understand the forces shaping our world. For most of history, we thought of lightning as a brilliant, fleeting flash from a cloud to the ground. But thanks to advanced satellites, we've discovered a class of lightning so immense it shatters our old ideas. This is the world of the megaflash. A megaflash is officially defined as a horizontal lightning discharge that spans more than 100 kilometers, or about 62 miles. To give you some context, a typical lightning bolt travels less than 10 miles. Megaflashes are in a completely different league. The World Meteorological Organization has certified some truly mind-boggling records. On October 22, 2017, a single flash stretched an incredible 829 kilometers, or 515 miles, from eastern Texas all the way to near Kansas City, Missouri. A commercial jet would take about 90 minutes to fly that same distance. Imagine a single bolt of lightning covering that much sky. And it's not just distance. Another record breaker, this one for duration, occurred over Uruguay and northern Argentina on June 18, 2020. That flash lasted for a staggering 17.1 seconds. These discoveries were made possible by a revolution in satellite technology. Geostationary satellites, like NOAA's OS series, are equipped with geostationary lightning mappers, or GLMs. These instruments watch entire continents continuously, documenting every single flash down to the millisecond, its start time, duration, and its full extent across the sky. This is a monumental leap from the old ground-based antennas, which simply couldn't see the full horizontal scale of these massive discharges. So, what kind of storm can create such a monster? Megaflashes don't come from your average thunderstorm. They are born from something far larger and more organized: mesoscale convective systems, or MCSs. An MCS is a sprawling, organized complex of thunderstorms that can persist for hours, sometimes even more than a day, and cover an area the size of New Jersey. These systems are meteorological behemoths, and they are responsible for a huge amount of rainfall in the tropics and mid-latitudes. The world has a few hotspots for these mega-flash-producing storms, most notably the Great Plains of North America and the La Plata Basin in South America. These regions provide the perfect atmospheric cocktail for them to thrive. The secret to a megaflash lies in the unique electrical structure of an MCS. A normal thunderstorm has a simple vertical structure with positive charge at the top and negative charge in the middle. But an MCS is far more complex. It develops extensive, horizontally layered regions of charge, especially in what's called the trailing stratiform area. That's the large zone of widespread, gentler rain that follows the main, intense line of storms. These vast, separated layers of positive and negative charge act like a gigantic natural battery spread out across the sky. A megaflash typically starts at a high altitude in the most intense part of the storm and then propagates horizontally, traveling for hundreds of miles through these charged layers. It's like a spark traveling along a massive, invisible wire in the sky. And they aren't just high-altitude events. That record-breaking 515-mile flash in 2017 actually produced over 100 cloud-to-ground strikes along its path. Studying these events isn't just about chasing records. The existence of a megaflash is a clear diagnostic tool. It tells scientists that they are looking at a highly organized, extremely energetic storm system one that likely carries other major threats like torrential rain, large hail, and destructive winds. While megaflashes are a spectacular sign of atmospheric power, there's a more subtle change happening that has a far wider impact on our lives. Shifting patterns of rain. This is a core focus of atmospheric hydrology, and the evidence is clear. A major study in the journal Science found that human-induced climate change has increased rainfall variability over 3/4 of the Earth's land area. Our day-to-day rainfall is becoming more volatile, which means we're seeing longer dry spells broken by more intense, concentrated downpours. This pattern is a recipe for a cycle of droughts and floods. So what's driving this? The first and most fundamental driver is a warmer, wetter atmosphere. The physics are simple. For every 1 degree Celsius of warming, the atmosphere can hold about 7% more water vapor. Warmer oceans evaporate more water into the air. When a storm system forms, it taps into this supercharged atmosphere, this bigger reservoir of moisture, resulting in heavier rain and snow. Climate models project this trend will continue. High-latitude regions, like the northern United States, are expected to get wetter, while subtropical areas, like the American Southwest, are expected to become much drier. The second driver is altered atmospheric circulation. The planet's weather is governed by vast, circulating patterns of air, and climate change is disrupting them. You've likely heard of El Niño and La Niña. These are natural cycles of warming and cooling in the tropical Pacific that can dramatically shift weather patterns globally. For example, El Niño can bring drought to Indonesia and heavy rain to South America. Scientists are now studying how climate change might alter the frequency and intensity of these cycles, adding another layer of complexity. Another critical feature of this circulation is something called an atmospheric river. These are long, narrow corridors of concentrated water vapor that flow from the tropics toward the poles, like rivers in the sky. A single one can carry as much water vapor as the Mississippi River. When these rivers of moisture make landfall, they unleash extreme rain and snow, causing floods and landslides. Climate change is expected to make these atmospheric rivers more intense because the warmer air will allow them to carry even more moisture. The series of powerful atmospheric rivers that drenched California in the winter of 2022-2023 is a stark reminder of their power. The third driver is surprisingly small: aerosols. These are tiny particles suspended in the atmosphere, from natural sources like dust and sea salt, or from human pollution like soot. These microscopic particles play a huge and complex role. They act as seeds, or cloud condensation nuclei, for water vapor to condense on and form cloud droplets. The type and amount of aerosols can completely change a cloud's properties. In some cases, pollution can create clouds with many more, but much smaller, droplets. These tiny droplets don't easily collide and merge to form raindrops, which can actually suppress rain. This is called the aerosol indirect effect. But it's not that simple. In other conditions, aerosols can make storms stronger. They can lead to taller, more robust clouds that produce more lightning and heavier downpours. Dark aerosols like soot can even absorb sunlight, warming the air around them and causing cloud droplets to evaporate, which again suppresses rain. This dual role makes aerosols one of the biggest sources of uncertainty in climate projections, but we know they are a major factor in the large-scale rainfall shifts we've seen. Finally, there's land use change. How we use the land has a direct impact on local weather. Cities, with their concrete and asphalt, create urban heat islands, making them warmer than the surrounding countryside. This localized heat can trigger or intensify thunderstorms and rainfall over and downwind of the city. Conversely, deforestation often leads to less rain. Trees are vital for returning water to the atmosphere through a process called evapotranspiration. When we clear forests, we break a critical link in the water cycle, which can reduce regional rainfall. So how do these two stories, the dazzling megaflash and the shifting global rain, connect. The link is the powerful storm engine that creates them both, the mesoscale convective system. The very same MCSs that produce the vast electrical architecture needed for a megaflash are also responsible for a massive amount of precipitation. In many parts of the world, these systems account for over half of all rainfall. So any change in how often these storms occur, or how intense they are, directly impacts rainfall patterns. Climate models predict that our warming world will see an increase in the frequency and intensity of the most extreme MCSs. A warmer atmosphere, supercharged with both moisture and energy, provides more fuel for these storms. Future MCSs are expected to be larger, last longer, and produce much more intense rain. This creates a direct link between our two phenomena. They share a common origin. The conditions that favor the giant electrical battery for a megaflash are the same conditions that support extreme rainfall. You can think of an increase in megaflashes as a symptom of a more energetic and intensified water cycle. Research shows a strong link between lightning rates, storm energy, and precipitation. As global warming drives up both energy and moisture, we can expect more lightning and more extreme rain. Some studies predict that lightning strikes in the US could increase by 50% this century. Aerosols also act as a common influencer. The same pollution particles that can alter rainfall efficiency also affect the charge separation processes that lead to lightning. So, in a way, pollution can simultaneously tweak a storm's electrical output and its rainfall. The science of atmospheric hydrology shows us a world where the tiniest water droplet and the most immense lightning flash are part of a single, interconnected story. Megaflashes and shifting rain are not isolated events. They are powerful signals that our planet's climate system is becoming warmer, wetter, and more energetic. The awe-inspiring sight of a 500-mile lightning bolt is a dramatic reminder of the forces at play. But the slow, relentless shift in where and how rain falls is a more insidious threat, capable of reshaping economies and ecosystems on a global scale. Understanding these connections is crucial for our future. By improving our knowledge of the processes that drive these extremes, we can better forecast them, mitigate their impacts, and adapt to the new reality of our changing climate. The electrifying dance of megaflashes and the changing cadence of rain are a clear message, written in the sky and on the land by the powerful forces of our atmosphere.